So with no further ado, I really want to thank Monika for bringing to us a broad overview of what's so exciting about the Topology 21 program. Monika, over to you.
Hi, thank you very much. Well, I'm very happy to give this lunch talk. So it will actually not give a very broad overview of the program, but rather like a very easy and intuitive description, that at least that's what I planned, into quantum simulation with cold atoms, and in particular quantum simulation of topological phases of matter. And well, I guess it's a very diverse audience, at least that's what I was told. So I don't know exactly what's the background of everybody. So please, if you have any questions or if you have any comments, feel free to interrupt me at any time. So my plan is to first motivate a little bit why we think quantum simulation is interesting, and we believe there's something that we can contribute to with our cold atom systems. And then I want to introduce our platform a little bit to tell you what cold atoms are, and then to give you an idea of how we use these systems in order to simulate topological systems, and in particular I will focus on quantum Hall. And so let me just start with quantum simulation. Why are we interested in doing that? And the basic motivation is to get a better understanding of quantum mechanical phenomena in the properties of materials. That's like the overarching goal. And then once we have understood these phenomena, of course, we would like to control them and maybe even design new materials with more interesting or more technologically relevant properties. So understanding quantum mechanical phenomena has a lot of technological applications. We may think about high TC superconductors, which have relevance for power delivery or magnetism, but generally for quantum technologies like building quantum computers, building quantum sensors, or building ever better atomic clocks. So all of these are examples where these questions are relevant. So now maybe what you may wonder is, okay, that's interesting, fair enough. We want to understand quantum mechanical phenomena, but what's the challenge? Like why is it more difficult than simulating any other classical phenomena that we may be interested in? And the challenge is really exponential scaling. And I may not have to explain that in times of COVID. Now I think everybody knows about exponential scaling, but nonetheless, I think it makes sense to have this very basic example in mind, that you may have like a crystal as in a material where you have particles that can be either in spin up or spin down, and just think about what the different configurations are and how many of them we have if we just count them. So let's just take an example of maybe 4 spins that can be either in spin up or spin down. So then we can arrange them in different orientations. So for instance, all of them may be polarized in spin up, or all of them may be polarized in spin down, but we can also have any other combination. So I can have 2 of them in spin up, 2 of them in spin down, and so on. And now if we count them, you find that there are 2 to the n possible configurations. Okay, but now our quantum mechanical system may be in a superposition of all of these. So if I just want to write down my quantum mechanical state that I call psi, then it's in a superposition and it has a coefficient for each one of these contributions. So it has some coefficient C1 for, let's say, this configuration where we have all of them polarized in up. Then there's another coefficient C2 for all of them being in down, and so on. So I have 2 to the n different configurations and coefficients that I have to save if I just want to write down what my many-body state is. Okay, so what does that mean? If we just look at the number and how fast it increases, then you find that for 10 spins, the number of coefficients is 1024. Now, if I double the number of spins, I'm already at something like 10 to the 6 coefficients. If I double it again, I'm at 10 to the 12, and so on. So if I simulate something like 300 spins, which is not all that much if you think about the number of electrons in a real material, then you are easily at something like 10 to the 90, which if you just want to write down the state, all the coefficients in your memory, it's almost impossible. And then you haven't even done any simulations yet. So this somehow highlights why simulating quantum mechanical systems exactly may be very hard. Of course, that's not always the case. What we should keep in mind is that sometimes we can make very efficient approximations, which allow us to do these simulations nonetheless, right? But generally, there's no efficient solution for simulating interacting quantum mechanical systems. And the only thing that we can do is simulate small systems, maybe with a few tens of spins, depending on the model and the dimensionality. Okay, so classically, this problem is really hard. So now the idea is, well, if we cannot manage to simulate these systems exactly, why not use a quantum simulator? And this idea goes back to Richard Feynman, who proposed that if we have a controllable quantum system in the lab, so let's just imagine I can build this from bottom up. I have my quantum mechanical particles, I arrange them in the way I want and make them interact in the way I want. Then I can just ask this quantum mechanical system directly. So for instance, I could perform some time evolution according to a certain Hamiltonian, or I could ask something about the ground state of this system. And then I just perform measurements. And if I want to know how these phases vary as a function of the microscopic parameters, well, if my system is very controllable, then I can simply tune those and see how the properties of the ground state phases change.
May I ask you, but if you choose, say, for example, your system to be in the maximal spin, right? Then there is no this many coefficients. Then you have just, one particular state. So you can start from this higher spin and then try to go down or whatever. I mean, if
Sure.
there is consideration of,
Sure. So for instance, that's a very good point. So for instance, I could choose, and actually, if I now think about this system, choose to prepare it in this state where all the spins are polarized, right? Where they are all in exactly the same state. So it's very easy to write down the state, no problem at all. But now I may want to do a time evolution experiment. So that's my initial state. Now I let it evolve according to some Hamiltonian. Now, of course, if there's no dynamics, it's not a very interesting problem, and you don't need a quantum simulator for that. If that's the ground state of your system, you're done. There's no question to answer. But the most interesting question is about time evolution. So if you let your initial state psi 0 evolve according to some Hamiltonian e to the IHT, right? And you want to know the evolution, sorry, this is psi 0 and this is psi of t, the evolution of your quantum system. Now you will acquire coefficients on other states. Like if this is not the ground state of your system, then it will connect to all of these other configurations, right? So the information will spread, and depending on how fast it spreads, the more or less complicated or difficult your problem will be. Does that make sense? Okay.
Yeah, go ahead, Monika. I think you're doing.
I didn't hear it very well, but
Another question, I think. Wait, Marcus?
Yeah, may I also ask, before I get lost, how is this different from the classical situation of a Ising model with n spins that also has 2 to the n states, and its state and phase space would be 2 to the n numbers that declare its probability density? Somehow this has to be more difficult, but I'm not getting it.
Yeah, so the difference is really the superposition, right? That my quantum mechanical system can be in a superposition of all of these different configurations.
Okay, so it's not a mixture, it's a superposition that makes everything much harder.
Right.
Thank you.
Okay, so now in order to solve this problem, we may want to build a quantum simulator. Okay, so how do we do that? Well, we first need some quantum mechanical particles that we can control very well. And there has been a lot of remarkable progress over the years in controlling single, individual, or even few ions, or maybe charge neutral atoms, Rydberg atoms, or superconducting qubits. But now the challenge that all of these platforms face is that we want to accumulate more of them. So we want to have large numbers of these particles, have a similar level of control or as good level of control as over the individual particles. And they should be interacting so that we have some interesting many-body system. We don't want to have isolated individual particles, because then it becomes trivial to solve the problem, and we don't need to go through this complex quantum mechanical calculation. And what we are working with is ultra-cold atoms in optical lattices. So now I first would like to motivate first of all, what ultra-cold means, why we have to go to these temperatures, and how we actually get there. Okay, so typically we work at temperatures that are in the microkelvin or nanokelvin regime, so 10 to the minus 6 to 10 to the minus 9 Kelvin. So this is a very low temperature scale if you compare to anything else that we know of in nature. And you may wonder why we actually have to go to these low temperatures. And so the easiest way to understand where this temperature scale comes from is to ask the question, how do we get from the classical regime, where our charge neutral particles just behave like an ideal gas, to the quantum regime, where quantum phenomena become important? So if we are at very large temperatures, much larger than some critical temperature, that is the scale that we are interested in reaching, then we are just dealing with some point particles, ideal gas, with some mean distance d between the different particles, and they can move around and they can collide if they meet each other. But now we know that in quantum mechanics, these particles also have some wave character, and this is calculated, or the size of this wavelength is given by the de Broglie wavelength, which depends on temperature. So the de Broglie wavelength scales as 1 over square root of the temperature. So if we cool the system to lower and lower temperatures, at some point, this length scale will become on the order of this interparticle distance d. So in a sense, these quantum mechanical particles start to see each other, and the wave packets start to overlap. And this is where quantum mechanical phenomena become important. So the temperature scale is related to the density of our system. So in order to see quantum mechanical phenomena, we want to reach a scale where this de Broglie wavelength is on the order of the interparticle distance. And for our densities, this means that we have to reach temperatures that are very low, on the order of a few microkelvin. So that's the very basic explanation why we have to go to so low temperatures. But now another question may be, how do we actually get there? I mean, we know that using dilution refrigerators or similar experimental techniques will not help us to reach the nanokelvin regime. Okay? We may be able to go to millikelvin, but that's basically all we can do. And what we use in order to cool our atoms is laser cooling. And the basic idea can be explained in one dimension, but then you can also extend it to higher dimensional systems. So let's assume we have a particle that moves at a certain velocity v, and we have an additional laser beam that is tuned near resonance. So we have certain internal transitions in the atom, but then the photons that we send towards the atom have a different frequency that is radically tuned. And this is important because now, due to the Doppler shift, those are in resonance with the atomic transition only if the atom is moving towards the laser beam. And now only atoms that move towards the laser beam will be able to absorb a photon and get a recoil kick. So by scattering many, many photons from this laser beam, the atoms essentially experience a pushback and get slowed down. And if this configuration is chosen in the correct order along 3 directions in space, we can manage to cool down the atoms along all 3 directions and reach the Doppler limit, which is on the order of a few tenths of microkelvin. So this technique of laser cooling actually allows us to get already to pretty low temperatures. Now, this is not enough. We need to actually get colder than that in order to reach this regime where the de Broglie wavelength is on the order of the interparticle distance. Now, in order to get there, we perform a second cooling step, which is evaporative cooling. So let's imagine now we have some additional trap. So we have our cold cloud of atoms, only microkelvin regime. And now we can trap them, for instance, using a magnetic trap or an optical trap. So we may imagine that now we have this thermal distribution of atoms that is in this trap. So we have some atoms that are at lower velocities, some at intermediate velocities, and some in higher velocities. And now we successively lower the trapping potential such that the hottest atoms, or the ones with the highest velocity, can escape the trap. So we lower the trap, we let the hottest atoms escape, and now the parameters have to be chosen such that rethermalization of the remaining atoms is very efficient. So by removing the hottest atoms from the trap and letting the remaining ones rethermalize, we can successively reach lower and lower temperatures. Of course, we reduce the number of atoms when we do that, but we reach temperatures that are then in the nanokelvin regime and allow us to realize degenerate quantum gases.
May I ask you at this point that let's say that these particles do interact with each other, okay? Not only with this external stuff, but between themselves. So I would be thinking that if the energy of interaction is larger than your temperature, then temperature is not important. You see that there is a kind of some limit for the temperature where energy of interaction is larger than temperature.
So you are speaking now of the first step or the second step?
No,
or just in general?
maybe even first step. That then when you're saying that this wavelength goes with low temperature, I agree. But then when energy of interaction becomes larger than your temperature, then I do not see why further decrease in temperature would help.
So for this regime, interactions are actually very small since the cloud is very dilute. This energy scale is small. However, actually there are some non-trivial phenomena. For instance, if you cool down this cloud to lower temperatures and increase the density of the cloud, then there are photon-mediated interactions. So there can be effects where the atom absorbs a photon, re-emits it, and may be absorbed again by another atom.
Yeah,
and
or just Coulomb interaction between them, right? For example, as well, if there is any, something like long-range interaction.
Well, we have basically contact interaction. So we have charge-neutral atoms. That so this is not a problem, but we have photon-mediated interactions, and this can actually lead to heating. So the temperature limit that is reached in this cooling scheme may be limited by the density. So you're right. You're right. It may be limited by the density.
Yeah.
But
I have in mind something like dipole-dipole interaction. Something which is long range, but I mean not maybe just Coulomb, but something else. Okay. Thank you.
So now in this evaporative cooling step, actually interactions are important for this rethermalization to be efficient. So if we remove the hottest atom by lowering the trap depth successively, we can reach a lower mean temperature after this cooling step. And if we get cold enough, so for bosonic atoms, we can generate a Bose-Einstein condensate. And for very low temperatures, so if we're close to 0 temperature, the easiest way to think about the BEC is a macroscopic occupation of the lowest energy eigenstate. So if we think about a harmonic trap, where this is the lowest energy level in the harmonic trap, then we have our ground state wave function, which will be just a Gaussian, and all the bosonic atoms will occupy exactly the same ground state wave function. So we can have 10 to the 6 or even more atoms, bosonic atoms, that are in precisely the same quantum mechanical state. Now, for fermions, if we cool them to low temperatures, the situation is a little bit different. So for fermions, if we really think about 0 temperature, then the system would look like this, that we have some Fermi energy denoted as EF, and then a 2-component Fermi gas, for example, will fill up all the energy levels up to the Fermi energy. So you would have spin ups. Now for equal spin mixture, spin ups and spin downs. And depending on the atom that we use in our experiment, we could work with either one of the two. So we could either work with bosonic or fermionic atoms. Now, once we had reached this regime of very low temperatures, we can trap the atoms in optical potentials that we engineer by interfering laser beams. And this effect is based on the AC stack effect. So what we do is we use now laser beams that are far off resonant. So previously for the laser pooling technique, we wanted the atoms to scatter many photons. So we chose a near resonant frequency. Here we are far resonant, so the atoms do not scatter any photons, but they feel a conservative potential, the dipole potential, which is proportional to the intensity of the beam. Now, this allows us to create optical lattices. For example, if we think about interfering two laser beams, which have the same polarization and the same frequency, they will create a standing wave, and the atoms see this as a potential landscape, and they want to accumulate in the minima of the potential. So they preferentially go to the minima of the standing wave. And then depending on the detuning, we can either make repulsive or attractive potentials, but in both cases, we can generate optical lattices. And for this simple configuration of two counterpropagating beams, this distance is on the order of the wavelength of the laser beam. So naturally, the scale, the geometric scale we are working with is in the micrometer regime. So these are very large crystals where our atoms move around. And now, depending on how we arrange these laser beams, we can generate a variety of different potentials. So we can generate 1D, 2D, 3D lattices, and even change this dynamically. Or we can generate more complicated ones like hexagonal lattices and etc. And more recently, people have also used other techniques in order to shape the intensity profile of laser beams. For instance, we can use large arrays of tiny micromirrors, which are also built in projectors, in order to project arbitrary potentials onto the atoms. And just to show you some fun pictures that we have taken in Paris, in the group of Jean Dalibard, if it works. I wanted to show you a few potentials that we have generated for our 2D rubidium gas. So these blue regions, those are atoms trapped in a potential that we projected from the top. So we have a light sheet from the side. It's a very thin bosonic cloud. confined in a potential from the top that we project, and we generate using this micromirror array. And as you can see, so this is actually a scale of 10 micrometer. You can arrange the atoms in any pattern that you want. So in this coffee cup, or like a rooster, or this ring-shaped potential. So this is a lot of fun, but it's actually also useful. So this ring-shaped potential we have actually also used for physics experiments. So it's not only fun to create these potentials, but we can also use it. Okay, so now back to optical lattices. So the idea is now that the atoms that move around in this periodic potential, they can be used in order to simulate important condensed matter model Hamiltonians, such as Hubbard models. So the idea is that these atoms that move around in this potential, they mimic the motion or the properties of valence electrons. And this artificial crystal that we have generated by interfering laser beams mimics the iron crystal in a real material.
I have a quick question.
Yeah, sure.
So this potential that you project from the top, is that a translationally invariant potential in the third dimension? Or can it have some modulation in the third dimension as well?
That depends. So in these experiments along the vertical direction, we had like another standing wave where the atoms were only sitting in one plane.
Mm-hmm.
You could imagine that you couple several planes. However, just technically it becomes a little bit challenging if you want to have a very high resolution for these potentials in plane, because then you are limited by the depth, by the focal depth of your high numerical aperture optical system.
But could you, for example, do something more topologically non-trivial, like I don't know, something with knots in it?
So you're thinking about something that is not translationally invariant in the Z direction, to have something more complicated. That's not so easy to do, actually. So
okay.
Yeah, and for some special cases, there are ideas out there, but it's generally not easy to do.
Thank you.
Welcome. Okay, so if we are looking at the system of atoms that are trapped in this optical lattice, so for a 2D potential, schematically, this may look like this. We just have lattice sites that are shown in gray, some tunnel coupling between neighboring sites that describes the kinetic energy of the atoms moving around in the potential, so they can tunnel between these neighboring sites. So along the x-axis, again, so this would be the potential, and this would be the tunnel barrier for the atoms to tunnel to the neighboring sites. And then there's an on-site interaction energy U if the atoms sit on the same site. So this allows us, or the dynamics of these atoms is actually described by Hubbard models. So we have this kinetic energy term minus J, this denotes hopping between neighboring sites, and then we have creation and annihilation operators for the particles moving around, and some interaction term for them if they sit on the same site. So these operators N count the number of atoms on a site, and A dagger and A create or annihilate a particle on a specific site in the lattice. Now this is the very, or the easiest model that we can do with bosonic atoms. But of course, we can also work with several or more than one component, and then the model is much more complex. But the basic idea is that we can use these systems in order to study phenomena that we know from condensed matter in an idealized situation. So we can directly implement and study model Hamiltonians that allow us to understand basic properties of condensed matter materials. Now, this is a simplified description due to many reasons, but one is that we completely get rid of any defects that would otherwise be present in a real material. We do not have any phonons, so there's no interactions between the particles moving around in the crystal and the crystal itself. And since we generated this bottom up in a vacuum system, it's very well isolated from the environment. So if we prepare a certain initial state and want to study time evolution, we can do this for relatively long times because it's very isolated from the environment. Now, I already mentioned before that the length scales are very different. So this is on the order of, let's say, a micrometer or half a micrometer. Now, if we compare this to a real material, that's of course much, much larger. In a real material, we would work with angstrom. So in our systems, the densities are actually very low. So for cold atoms, we have densities on the order of 10 to the 14 per cubic centimeter, while for real materials, we have something like 10 to the 24 or 10 to the 25 per cubic centimeter. And now if you keep in mind what I've told you before, that we actually want to reach a regime where quantum mechanical phenomena dominate and where we want to have a temperature scale or de Broglie wavelength that is on the order of the interparticle distance, you have an idea why, in order to see similar phases of matter, we actually have to go to much lower temperatures as compared to real solid state materials. So due to this very low densities, we work at temperatures that are on the order of a few nanokelvin, while in solid states, the complement would be on the order of millikelvin or even Kelvin. Yes.
Maybe you plan to explain this, but I'm burning to ask a question. Is there any reading in this system? Do I know if a place in the trap is occupied or not?
So you are asking if, for instance, if we look at this periodic potential, if I have a way in order to measure if one side is occupied by a particle or not. Okay, that's a very good question, because I just wanted to show you some images that have been taken with a quantum gas microscope where you can see precisely that. So due to this large length scale, so first of all, it means that we have to go to lower temperatures. But on the other hand, we have this very enlarged model system where we can now build microscopes that allow us to resolve individual lattice sites. So what can be done is actually to trap these atoms, so to freeze their motion. If you want to detect where an atom is sitting or not, we first freeze the motion and then we take a picture. So this projects the quantum mechanical state to the number basis. And then you can take images like this, where each individual dot is an atom that scatters many photons. So we shine in resonant light. The atom undergoes a few absorption and emission cycles, a few hundred ones, and then we can collect these fluorescence photons onto a high resolution, with a high resolution imaging system onto a camera. So this is actually taken from Immanuel Bloch's group in Garching here in Munich at Amplitude. So here, each individual dot is actually a single atom that emits a few hundred photons. And you can already see that it's possible to distinguish atoms on neighboring sites. So actually here, these are two atoms that sit on neighboring sites. So the point spread function here is on the order of 700 nanometers. It's a little bit larger than the lattice constant, but nonetheless, in this imaging system, you can reconstruct the whole density distribution. And then if you want to take statistics of the particle number distribution, you just take many of these images and evaluate like the mean atom number per site and the fluctuations or the variance of the site occupation. So yes, you can image or detect how many atoms are there per site. And for fermions, for example, if you work with two different internal states, there are also now ways in order to get spin resolved images to know which fermion was in spin up and which one was in spin down, for example. So get full spin and density resolved images.
So in principle, if I have a reading, I could reintroduce phonons into the system, no? By introducing some feedback between the presence of the atoms themselves and what is confining them.
Yeah, so that is actually a very interesting direction. There are many ideas and proposals out there on how to do that. It's not very simple. So there are ways to do it, but there are several technical challenges, I would say, that are associated with it, but in principle it's possible. Okay, so now I spend a lot of time on our platform, so I'm not sure how much I can say about topology. But anyway, I will start and then we'll just see how far it goes. Okay, so one field that we are very interested in contributing with our quantum simulation experiment is topology, or one way how to generate topological bands is by mimicking magnetic fields, so by generating artificial magnetic fields. And I wanted to explain in particular this topic because I think it's very intuitive to understand how we generally approach such a problem. So generally, we have like a model of interest that we want to study. So you know the Hamiltonian that describes the physics, and then you try to find experimental techniques that allow you to simulate this model in the lab. And the maybe easiest way in order to motivate how at least one of these techniques works is by reminding yourself about the quantum Hall effect and what's the topological properties about the quantum Hall effect. So if we think about a basic Hall bar geometry, we may have something like this in mind. So we have two-dimensional electron gas in here, in this Hall bar geometry, which we expose to a perpendicular magnetic field, and where we send a current through, which is here denoted as IXX. And then we can measure different voltages. We can measure the longitudinal voltage or the transverse Hall voltage. And from this, we can also calculate the transverse Hall resistance. And we know that classically, there is a linear dependence between the applied magnetic flux or this applied magnetic field perpendicular to the Hall bar and the transverse Hall resistance. So this is the regime on the left side of the dashed line. So this classical regime where we have this nice linear dependence between the applied magnetic field and the transverse Hall response. Now, if this two-dimensional electron gas was cooled to very low temperatures and the sample is reasonably clean, and we crank up this magnetic field that is subject to the Hall bar, then we find that the behavior starts to deviate from this classical case, and there are these plateaus that appear in the transverse Hall resistance. Now, these plateaus by themselves may not be so super interesting. What makes them interesting is that these values are extremely precise. These values only depend on natural constants and an integer number. So that if we just look at the plateau values, Rxy is given by 1 over I, where I is just an integer number, and then h divided by e squared. So that's all there is, and it does not, as you see, depend on certain material properties or microscopic details of how I shape my Hall bar geometry or anything like that. It's precisely given by that value and has been measured very precisely in the lab and has been used already for a long time as a standard for resistance measurements to compare also between different labs. And you may also know that this is one of the ingredients that was used for the redefinition of the SI units in 2019. So now these integer numbers, they are actually related to the topological properties of the energy bands that are occupied with electrons. So the reason why these plateaus are so well quantized has its foundation in the topological properties or the Chern numbers that characterize the energy band. So if I want to calculate this integer number I in a very simple case in this non-interacting picture, then I have to sum up all the Chern numbers of the bands that are occupied with electrons. So all the bands below the Fermi energy. And then this number simply allows me to calculate the transverse Hall resistance. Okay, so now this is very abstract. I somehow now have this topological invariance, but the question is, what are there? Like, how can I think about these topological invariants, the Chern numbers? And I'm very sure most of you have seen this analogy to geometric objects, but nonetheless, I think it's very useful to keep this picture in mind. So this is the usual picture on how to explain topological classification of geometric objects. So here you see like a mark and a torus, which have genus 1. They belong to the same class. And there's a sphere which has genus 0, which is in a different class. Now, mathematically, you can actually calculate these invariants by integrating the surface of the object over the whole surface, like over the whole sphere. You can assign a local curvature to each point on the surface. You integrate over the whole thing, and then you can assign an integer number to your geometric object. And this connection that you integrate over a local quantity, but a closed manifold, which allows you to assign an integer, may also give you an intuitive understanding why, if you now start to slightly deform the surface, it does not directly change this integer quantity that you get out. If you want to change that integer quantity, you have to do something a bit more violent, which is like punching a hole through the sphere, for instance, in order to change its topological class. And very similar for crystals, we can calculate an invariant that classifies the topological properties by integrating over a local curvature. Now, for these geometric objects, the space that we are interested in for the integration is real space. We just define our curvature, our local curvature for the surface. For periodic systems or for crystals, we do that in quasi-momentum space. Okay, so for crystals, this integer quantity or the Chern number is defined as 1/2 pi, and then we integrate over a curvature, the local curvature, which is defined in quasi-momentum space, where here Q denotes the quasi-momentum here for two-dimensional crystals, so it would be Qx, Qy, and we integrate over the whole manifold, which in our case is the Brillouin zone. So this defines the topological properties of an energy band. And now, similar to the picture that we have in mind for geometric objects, that we can deform them and that doesn't really change all that much, stays in the same classification. We have to do something violent in order to change that classification. Something similar happens for periodic crystals, where now this violent operation would be that we need to close an energy gap in the spectrum. So this Chern number is very well defined for a band that is separated by an energy gap from the higher lying or lower lying ones. But then the invariant can change if you vary a parameter, and once you vary the parameter, there's a gap closing point in the spectrum. Then the Chern number can change from its previous value to a new value. And then this local curvature is actually defined according to the eigenstates. So you can calculate the eigenstates of the system, write them down as a function of quasi-momentum. And then the Sperry curvature basically tells you how these eigenstates change as a function of quasi-momentum. So to give you the definition, it would be the derivative along Qx for this eigenstate u, derivative Qy, eigenstate mu, and the reverse. For those of you who are interested, but it's not very important. So u are here the eigenstates, the cell periodic Bloch functions. So it somehow tells you how the eigenstates wind as a function of momentum, as a function of quasi-momentum. Okay, so now having this example in mind, the quantum Hall effect and why the topology of the energy bands has profound consequences on the electronic properties, that is this nice quantization of the transverse Hall resistance, you may get an idea of how we may use this in order to quantum simulate a similar model. So you may actually say, okay, now we have our cold atoms in that lattice. We could apply a magnetic field to our system in order to see a similar phenomena, because the key ingredient for our two-dimensional electron gas here was the magnetic field. But now, since our atoms are charge neutral, it doesn't work as simple as that, because they do not experience a Lorentz force. So instead, we have to do something else in order to mimic the presence of the magnetic field. And an intuitive way to understand how that works, or how the scheme that we want to implement in the lab originated from this idea, is to look at the Aharonov-Bohm effect. So typically, if we think about classical physics, we know that the vector potentials, they don't really play any role because they don't have any observable consequences. If we measure a physical observable, it only depends on the magnetic field and the electric field, but not on the vector potential A that generates the magnetic field. Okay, so this vector potential A is not observable. However, if we think about the Aharonov-Bohm effect, where we build an interferometer around a region in space where we have magnetic flux, then we can understand what happens and how we use this for our simulation. So what you see here is like a Gedanken experiment, where this is an infinitely long solenoid, where we have a magnetic field inside this region of magnetic flux. And then we can think about an interferometer where we start with a wave packet here, and we make a superposition between two different internal states, for example, and we make it propagate around two different paths. And then we read out the relative phase at the end of this interferometer sequence. And what the effect of this vector potential is, so I should mention one more thing. So actually the magnetic field is 0 in this region outside here, but the vector potential is not. And the vector potential A actually has an impact on the wave function that travels around these two paths around this region of magnetic flux. The wave function acquires a phase that depends on the vector potential. So if I write down my state psi for these two different paths, gamma 1 and gamma 2, then at the end of the interferometer sequence here, they will be different. So psi after the path gamma 1 will be some phase ETVI phi 1, my initial state psi 0. And this is not the same as my wave function that propagated along the path gamma 2. This one will acquire a different phase phi 2, which will depend on the vector potential. And now if I write down the relative phase difference at the end of my interferometer sequence, which I can measure, it will be proportional to the charge of the particle divided by h bar, the Planck's constant, and then the integral around a closed loop of this area of the vector potential, which is nothing else than the magnetic flux that is piercing the area of the interferometer. But now this is very nice, because if I keep that in mind, okay, so I have a magnetic flux which is related to a phase, and a phase that may be something that I can quantum simulate with other means. So I can now think about other experimental methods that allow me to mimic this phase, which is nothing else but a geometric phase. So I don't need a vector potential in order to get that phase. I can use any other technique in order to engineer it. And then if I have this finite phase difference around the closed loop, I can interpret this as a magnetic flux. So let me be a bit more precise in terms of the periodic potential or the lattice that we are working with. Okay, so now let's look at a square lattice, non-interacting, so we don't consider interactions between particles, where we have hopping between neighboring sites. Now, if you think about electrons that move around in this potential landscape, they can hop between neighboring sites. And we also have a magnetic field that is piercing the unit cell on top of that. What happens is that these hopping matrix elements become complex. So they acquire phase terms, which are the so-called Peierls phases. And these phases, they are essentially discretized versions of what we have seen in the Aharonov-Bohm effect. So if I calculate, as in the Aharonov-Bohm case, the relative phase a particle would acquire around a closed loop here, all I need to do is sum up the different phases on the bonds. Okay, so let me show you this schematic. So now let's assume we have these complex hopping matrix elements in the lattice, and all these phases are different. So they depend on space. So phi 1, phi 2, phi 3, phi 4, they are all different. Then the flux in this geometry that is piercing the unit cell is given by the sum over all of these phases. Okay, to be more precise, that's actually the phase the particle would pick up, the Aharonov-Bohm phase, and we can relate that to a magnetic flux that is piercing the unit cell. We've expressed now phi naught is the magnetic flux quantum h over q. Now, since we do not have any charge in our experiment, we usually use this Aharonov-Bohm phase as a synonym for the magnetic flux. Okay, so the goal for realizing quantum Hall systems is to generate artificial magnetic fields by making these hopping matrix elements in the lattice complex. And normally, if you don't do anything else to your system, these hopping matrix elements are real. So you have to find some other technique that allows you to make these hopping matrix elements complex. And maybe as a side remark, since we will engineer these phases directly, they are usually on the order of 2 pi. So this flux per unit cell is naturally on the order of a magnetic flux quantum. And this is actually very large. So if you compare it to a real solid state material, where the distances here are in the order of angstrom, in order to reach the regime of a magnetic flux quantum per unit cell, you have to apply a field that is several thousand Tesla large. So this is very difficult to reach in a normal system. But of course, also in solid state, there are other ways, like using super lattices, for example, in order to reach similar regimes by enlarging the unit cell of the system. But in our case, it's relatively simple to reach this limit of very large magnetic fields. Okay, so maybe in the last 5 minutes, then I think I probably have to stop. I at least want to show you very briefly how the technique works, and then one experimental result, which is a little bit old, but nonetheless, I think it's insightful to look at it because it's very nice and if you keep this artificial magnetic field picture in mind. Okay, so how do we actually do that? We realize these complex hopping matrix elements by what is now called or known as Bloquet engineering, which means we take our Hamiltonian parameters and vary them periodically in time. So there's an example that I can give you for a 2-side model, so just a single double well, which has lattice sites A and B. We have a hopping matrix element J between neighboring sites. And then initially, we apply this potential energy difference, which is large, such that atoms can actually not hop around. They would have to pay a large energy penalty. But now we can apply a periodic modulation, a potential energy offset that will vary in amplitude to the left side, for example. So we apply a periodic modulation with some amplitude and some frequency and some phase. And if we choose this to be resonant, then atoms can absorb energy from this periodic modulation and hop to the neighboring site. But now there's actually an effective description of this periodic driving according to Fouquet's theorem, which allows us to, if we look only at stroboscopic time evolution, to describe it according to a new effective time independent Fouquet Hamiltonian HF, which is time independent. So stroboscopic times, I mean that the evolution time is an integer multiple of this driving period t, which has a new tunnel coupling, J effective, which is proportional to the original tunnel coupling J. And it goes with the Bessel function of the first kind, the argument V0 over H bar omega. So it's some renormalized effective tunnel coupling. But the main point is that it now also acquires a phase, which is related to the phase of the periodic modulation that I've applied. So now the only thing that is left for me to do is make this phase dependent on the position in the lattice. such that if I think about it as closed loop Aharonov-Bohm phase, it does not average out to 0. So the sum that I calculate should be different from 0. So this can be done. So we engineer this spatially varying modulation, or this is spatially varying phase, which allows us then to mimic a square lattice with a flux, homogeneous flux phi. And now the first experiment that we actually did in order to see that this is indeed the case, we tried to mimic cyclotron motion of electrons. So you know that if we think about a charged particle or electron in a magnetic field, it performs a cyclotron orbit. So in homogeneous space, it would just go around in an orbit. And we tried to see a lattice version of that. So a highly discretized version. We created individual plaquettes, so just isolated 4 sites like this. And we loaded a single atom into this plaquette. So really the lattice consists only of 4 sites, and we now prepare a single atom which is delocalized over the left bond. It's an equal superposition between A and B. And first of all, in this initial state, it does not tunnel. But now we can perform a quench and let this atom tunnel to the right bond. So, or we just make it symmetric and we let the atom tunnel to the right. Now, if there's no flux, what happens is that the system undergoes radial oscillations between the left and the right bond. It would just tunnel back and forth. There's nothing else that happens along the perpendicular direction. But now what you know from electronic systems in a magnetic field, there's something like a Lorentz force. So you would expect that due to the spiral motion, it would start to be deflected also along the perpendicular direction. It should make some chiral, should follow some chiral orbit, even though we are in this highly discretized space. So what we do is we quench the system, we let it tunnel, and at the same time we switch on the magnetic field. And then we track the mean position of this atom in the plaquette as a function of time. And what we see is indeed such an orbit where, let me explain you what you see. So on the left, that's actually t equal to 0. So the ideal initial state would be that the atom is delocalized along y. So this corresponds to mean position 0 on that axis. And it's fully on the left bond, which would correspond to minus 0.5. So we have some imperfections in our initial state preparation. That's why we start over here. Now, without any magnetic field, it would tunnel along this horizontal line. There would be nothing else. It would just go back and forth between the left and the right bond. But now, due to the presence of this artificial magnetic field, we see that it performs some kind of orbit which resembles a cyclotronic motion of a charged particle in a magnetic field. And from this behavior, we can actually directly fit the value of this artificial magnetic field that we have generated in the lab. And for this specific example, we got something that's on the order of 0.73 times pi over 2. So this is a very large magnetic field that we have generated, which is 1/4, I think, of a flux quantum, well, almost a quarter. And yeah, with this, I'm probably at the end, just to mention, which I find very cool. You can also use this system in order to really make a Hall deflection experiment and mimic this quantum Hall bar type of experiment in our artificial quantum systems. Okay, well, thank you very much.
Thank you, Monika. It was a beautiful talk. Thank you so much. I'm seeing applause.
Yeah.
Maybe also hearing it. More questions for Monika, please. If anyone has any. Thanks for taking the question so gracefully, Monika, during your talk.
Well, no problem at all. I'm happy to take questions during the talk. That's always fun. Yeah.
So I have a question. Great talk. Thank you. And a beautiful experiment at the end. When you change the sign of your magnetic field, you see the, do you see the electron going around in the other direction?
Yeah, exactly. Yeah.
I see.
We did that experiment. Yeah.
I see. And this 0.73 value that, so you calculated it using all the parameters of the experiment, and I guess you could match it to, what would you match it to? Something like the cyclotron frequency, or? something like that? Yes, the cyclotron frequency, right?
Yeah, so in our case, this value here is very simple to calculate. It's basically just to the geometry that we choose. So I told you that the phase comes about due to the space of the periodic drive.
Mm-hmm.
And now in 2D, basically what we do is that we have a periodic modulation with a phase that is different on this side, and this side. So, and sorry, one more thing, we have actually only implemented complex hopping along X. So along Y, we have real hopping. So now the flux or the phase for one unit cell only depends on the phase difference of the driving that you have applied here and here.
Yep.
So this you can immediately get from the geometry that you have chosen in the lab, which we can then compare to the value that we got. And just to give you an idea of how we did that, so we actually apply two laser beams that interfere. So these have slightly different frequencies, omega-1 and omega-2. They create interference pattern that has a phase that is moving or varying across the lattice. And this varying phase, which is given by the wave vector difference, sorry, we also choose resonance, right? So this is now equal to the energy offset delta, just to implement the resonance condition. This wave vector difference K times R gives you how the phase changes across the lattice and allows you to directly extract the value of the flux, which is very close to this value. We have actually chosen, so just as a side remark, pi over 2 exactly, but due to the partitioning of the lattice in these plaquettes, there was a geometric squeezing, and so the phase is a little bit different compared to pi over 2, but it's purely geometric. So
I see. But can you match it with the frequency of the motion that you see that you're showing on this slide?
Yeah, so this, of course, it's not a nice orbit, right? Because of the discretized positions. But I didn't put the plot here, but it's a very simple evolution, right? It's just one particle slide. So we have calculated the orbit and fitted the orbit to our data in order to extract that value.
Oh, I see. Super. Thank you.
Welcome.
Great. Okay, well, thank you, Monika. So next week, we'll hear from the Films 21 program. So all of you from Topology 21, please come, and hopefully we'll see all the locals. And then for the following 2 weeks, we'll have locals lunch for those who want to hear what the graduate fellows have been up to. So we've got a pretty full calendar for the rest of June. So thank you again, Monika, and see everybody next week, hopefully. Take care.